Yeah, those good times. Okay, so the second derivative test we use to find if it's a local max or local min. So let's talk about things here. So what does this mean if f prime of c equals 0? Just by looking at that. So yeah, so at c we have a horizontal tangent, a slope of 0. So at c we have a slope. So here we go. See that at c? Slope of 0. So if that happens, and what does this mean? Second derivative, which tells us what? So this saying it's concave up. So we have a horizontal tangent at C, and it's concave up. Then at C, it has to be a max or a min? A minimum. It has to be a minimum. So then F has a minimum at C. Right. It's just more finding our local max mins. Okay, so this guy, what does this mean? Again, when our slope equals 0 at C, and what does this mean? Second derivative of C is less than 0. Means we have, it's concave down, then we have to have a maximum. Right, so you have your concave up is positive, concave downs are negative. He's so sad or mad. Okay, so note the critical values for the second derivative are difficult to interpret. There could be a change in concavity as well as a local max min, but not necessarily. We cannot tell for certain unless we look at the first derivative test. So yeah, if you want to know more information to graph, this is going to be just a quick test to figure out if it's a local max, local min. Okay. All right, so let's look at this problem here. Find local max mins for this guy using two methods. So let's first use the first derivative test. So first derivative test. So this is the old school method we've been used to. So how would we find if we have a local max min before? Derive it. It's so much fun now, hey? It's so easy. It's like multiplication. That's all it really is. Okay, 6x minus 2 times 3 is 6x squared. Factor out a 6x, which is 1 minus. Yeah, this is that common theme. That where you like factor out and then you take it out again. Like, why am I doing this? Or you expand everything and then you're like, wait, I need it in factored form. You're like, oh, I did all that work for nothing. Okay, so we want when this guy equals 0. So what are our critical values? 0 and 1. So then we do our beautiful number line. We label it f prime of x so that we know like what's what when the teacher goes to market. Right? It's like a proof. So I'm not guessing which one's which. Okay, and then we have to do an interval test. So this is what we're going to learn about today is how do we avoid the interval test. Okay, so here we go. Plugging in, choose a number less than 0. Negative 1. Yes, I love when you choose simple numbers. 6 times negative 1 is going to give us a negative. 1 minus negative 1. Positive and a negative would be negative. Okay, 0 to 1, so 0.5. 6 times a half, 3, which is a positive, and 1 minus a half would be also positive. Okay, and then the last one, we did like 2. 6 times 2 is positive, 1 minus 2 is negative, so then we get a negative. Okay, so then we can finally say, looking at if we have a decrease, increase, decrease, what do we know? Local min, where? 0, and plug that into the original. 0, 1. Okay, and local max, f of 1, which is 1 plus 3 minus 2 is 2. Yes? It's a cubic.
No, I mean, no, but when we were talking about the derivative.
Oh, yeah, yeah, here's a squared, so it's going to be, once you know the first, yeah. If it's a polynomial quadratic, right? If there's a rational expression, now we have to really do our plus minus. Okay, so that's method 1. You know how to do that, right? So what's the second derivative test? Well, this is what we do. The first steps are the same. So let's leave it, right? So this is the same up to here. So we're here is the same. Up to here is the same. So we still find our critical values. Now, the second step is different. After we know our critical values, we're going to sub them into our second derivative. So, first of all, what's my second derivative? Going back to here. 6 minus 12x. Okay, so we're going to take our critical values. We're just going to sub them into our second derivative. So we're going to plug in 0 and 1. So plugging in 0 into my second derivative, 16 minus 12 times, oops, not 16. Dyslexic, I think a little bit. I think I really am. I truly believe that. Okay, what does that give us? Positive or negative? It's going to be a positive. If it's positive, that means it's concave up. So that tells us it's a minimum. Yes. So right away we know local min at f of 0. We still plug it in and we get 1. Next guy, plug in the other critical value. So 6 minus 12 times 1 will give you a positive or negative? Negative. So therefore he's concave down. Therefore he will be a local max at f of 1, which equals negative, negative 2. Positive 2? Plugging into the original, right? Getting the actual point. Yeah, sorry. Okay, so it's a way to avoid doing an interval test to find your local max and mins. So you're allowed to use this method. Try it again. Okay, so this guy, let's rewrite him. Okay, so find the local max and mins using the second derivative test. Nothing. Yeah, really? Yeah, nothing. Okay. Yeah, so let's go on. G prime of x, let's find our critical values. 2x minus 16, x to the negative 2. How would we get the critical values of this guy? What do we have to do with him? Factor out x to the negative 2 and x to the negative 2. Is it like a little fuzzy today? I feel like, yeah, I don't know. All right, so if I divide 2x by 2x to the negative 2, we're going 1 minus negative 2 with our exponent. So it's x cubed minus 8. Okay. It is. Yeah, let's not make this more complicated than it needs to be. What are my critical values? 0 and positive or negative? Positive 2. 0 and 2. Okay, so instead of, like I want to find if this is a local max or min, each one of them. So instead of doing an interval test, what are we going to do? Put it into the second derivative. So what is the second derivative? Let's start from this guy. 2 plus 32 x to the negative 3. You might even want to just write this as 2 plus 32 over x cubed. Guys, okay, so we're going to plug those into our second derivative. All right, starting with 0, positive or negative? Can't divide by 0. Uh-oh. So it's a vertical. Is it a vertical asymptote anyways? Yeah. So does not exist. Let's look at the original. Vertical asymptote. So go back to your original. D and E? Okay, let's try 2. 2 plus 32 over 8. Positive or negative? Positive, therefore it's concave. Up. I like to, well, U is like, shows you the up, so therefore it's a local min. Local min, G of 2, we have to go back to the original, lucky us. 2 squared is 4, plus 8 is 12. Yep. Oh, we have to find a lot of things to do that. So we know there's a vertical asymptote at 0. Well, we didn't find where there's increase, decrease necessarily. So we know there's a vertical asymptote at 0. Okay, I know that there's a local min at 2, 2 and 12. That's a minimum. So it's probably going like this. Right. Yeah, and then this side, I don't know if it would probably be, we'd have to do second derivative test, yeah. Like, so this could be a test question, but what you'd have to do is find your, find where it's increasing, decreasing, find where it's inflection points, all that good stuff, right? Where are my intercepts? This guy, not an intercept, that makes sense. And go from there. Okay, do you want to try the next guy on your own? Okay. So I'll start working through this. So your critical values you should have had as 2 and negative 1. And so when you plug in 2, you get positive, so concave up. So therefore, that's a local min. At 2, what did you get? What was the point at 2? Negative 2, thank you. When you plug in negative 1, you get a negative. So that's concave down, so you know it's a local max. And I believe it's negative 1 and 25. And that's what we should get. Okay. Question for you before we go on to the next answer. If you have a critical value for f prime of c equal to 0, and you plug it into your second derivative and it gives you 0, what's happening? So let's talk about this. What does this mean? It's your horizontal slope or slope of 0 at c. And then this means it's a, what do we call this? An inflection point at c. So give me a situation, like I have a horizontal tangent in c and an inflection point at c as well. So here's my c value. Okay, so an example of that would be, right, would be something like that. So it's also an inflection point. So it's neither a max or a min then, if you had like a cubic. So it can have a horizontal tangent and also be an inflection point. Okay, that can come up. So if you get 0 in your second derivative test, you know it's neither concave up, concave down. Therefore, it's not a max or min. Okay? Just okay. Find the maximum values of this guy. So let's take what we've learned and apply it basically. And we're going to use our second derivative test here. Find the maximum values. Yep. Actually, for a very short answer, maybe. Like on your log, it might be one worth 2 marks. Use a second derivative test to show where your local maximums are. Yeah. It wouldn't be like in your long. In your long one, you can do either or. Yeah. Find maximum values of this function. Use these together with concavity and points of inflection to sketch the curve. Okay. Well, right away we know what type of graph is this. Close. Quartic, right? It could be as exaggerated as that, degree 4. So domain of this graph should be negative infinity to infinity, right? Okay, so that you want to have a picture in your head of what it should sort of look like, if possible. So let's go ahead and start with our max mins. Okie dokie. So that is which which derivative? 1. 4x cubed minus 24x squared. We can factor what out? 4x squared. X minus 6. Okay, critical values 0 and 6. We're going to use our second derivative test here. SDT. Okay. No, it's close. Okay, 12. So our second derivative, 12x squared minus 48x. So we're going to plug in which values? 0 and 6. So plugging in 0, positive or negative? It's 0. So that means neither local min nor local max. It's probably like that, right? Cubic type situation. Try 6 now. I might need my calculator for that guy. Positive or negative? Yeah, it's most likely. Well, it could be either or. Positive, so therefore it is local min at, we have 6, comma, now we have to go back to the original, plug in 6. Okay. It's probably a really big number. Negative 432. Do we agree? That is really low of a number. Okay, so max or min's done. Now we want to see where it's concave up, concave down. We're going to find intercepts. What do you want to do first? Intercept? Sure. Okay, this guy's easy. Start with who? X or Y? So y-intercept, plug in 0, we get 0. X-intercept, what can we factor out? X cubed, we get x minus 8, so therefore we get 0 and h. Okay, so we have that done. Let's go to to our concave up, concave down. We already have our second derivative. We found it earlier. That's the nice thing about using the second derivative test. So what can we factor out of this guy? 12 and x. X minus 4. Okay, so critical values here, 0 and 4. So okay, so we know a second derivative. This is where concave up, concave down. Guys, are you copying this down? Like, what's going on? That's cool. You stay with the question. Okay, no, let me see your piece of paper. Yeah. Okay. -1, so we get a negative times a negative, which gives you a positive. Then we have positive and a negative, which is a negative, and then last, two positives. Okay, so what do we call 0 and 4? What are those called? They have a special name. Inflect, or for some of you, point of inflection. So inflection point at 0 comma something and 4 comma something. So 0, 0, and when we plug in 4, that's going to be a big number. Negative 256. Let's give it to you. Do you know where we're plugging that into to get that? The original. We want the actual y value. Okay, we also want to know where it's concave up, concave down. So concave up, so concave up, negative infinity to 0, union 4 to infinity, concave down, 0 to 4. Okay, so we didn't do increase, decrease. Let's see if we can figure it out without it. Yeah? What do you mean? Thanks. Okay. Okay, so let's see what we can do if we need to find our increase, decrease, or if we can use our local min and our concave up, concave down to figure out the rest. Okay. So we have to plot some important points, roughly. Okay, very roughly. So what are the x values that are important? Craig, can you move over here, please? So what x values are important that we found out? 0 and 8. 8. Yep, 8. 7, 8. 6 was important. 4 was important. 0 was important. That's pretty much it. What? Oh.
Well, we'll just pretend that.
No. 3, 4, 5, 6, 7, 8. There you go. That's better. Okay. What y values were important?
0.
Negative 432. Negative 100, 200, 300, 400. So we'll make this negative 432, as well as approximately to negative 256. Okay, let's start with plotting the points we know. Okay, so we know our y-intercept is 0, 0. We know we have an x-intercept at 0 and 8. We know we have a local min at 6 and negative 432. Okay. Inflection point is 4 and negative 256. So I'm going to label that as inflection point. So inflection point, this is a min. Okay, so we also know it's concave. So from 0 to 4, concave up or down? Down. So this is concave down. So I'm going to, one thing you can do, is there a gray? Maybe a pencil, right? So we know we're concave down to 4, and then we're concave up from 0 to 4. We're concave up over here and over here, and so forth. Okay, just to give me an idea. We know it's chordic and we know it's opening up. So do we know where it's increasing, decreasing? Can you figure that out from this graph? Yeah, it's going to be decreasing until our min, and then increasing otherwise. We could also do a critical value test if we need to. Okay. If I ask you to show where it's increasing or decreasing, then you need to show that. Do the interval test. Okay, so let's try and sketch this. This is concave up until our flexion point. Oh, I don't like that color. Sorry, I want it to be different. Yellow? Do you think it'll stand out enough? Okay, so let me see if I can do this well enough. So concave, oh, that's ugly.
You can do it.
Let's try it again. Oh yeah, woohoo! Okay, concave up, and then concave, no. Is 0 an inflection point? Yes. Oh, I didn't label it. See? This is why it helps to label. Oh, I lost my yellow. There it is. Okay, now it's concave up until 8. So up until 8, and off I go. Beautiful. Okay, do you see when I say rough sketch? You still have to show the critical points, but you don't have to it's still pretty rough, right? Like obviously my scales aren't the same, things like that. Things like that. Okay, just like yesterday, if you finish in class, do this every day. For that assignment, you can go. That's going to give you motivation. It's always been a thing, I just didn't announce it. So, from this day forward, okay, this will give you, if that's the carrot you need, then that's the carrot you can have. Okay? Okay, so oh yeah. Okay, so it's not page 232. 1, 2, and 3 left columns of all of these. So 1, 2, and 3 left columns. Greg, do you understand what a left column is now? Yeah? I like that yellow. The mustard yellow. This is the color I've been using in my house. It's like grays, like neutrals, and then just a accent color. I love it. And people hate it. That's okay. I just love it. Just so you guys needed to know that.